Chapter 4. In this chapter we're going to study a model that describes the bonding in covalent compounds. And there's two components to it, Vesper and valence bond theory. We'll start with Vesper, valence shell electron pair repulsion theory. To this point we have drawn Lewis structures of molecules without attention to the three-dimensional arrangement of atoms in a molecule. Now Vesper is a simple model that predicts with pretty good success the three-dimensional shape of a molecule. So we've seen that atoms are bonded together in covalent molecules by shared electron pairs. And electron pairs, or electron clouds as I'll refer to them, being of the same electrical charge, they're all negative, they will repel each other and move as far apart as possible from each other in three-dimensional space to minimize their repulsions. Here are some diagrams that show the arrangements in space of various numbers of electron clouds or bonds around a central atom. If we have only two bonds or two electron clouds, as in beryllium chloride, the three-dimensional geometry would be linear with a bond angle of 180 degrees. Here's an animation of a linear molecule, beryllium hydride. So beryllium has two electron clouds around it 180 degrees apart, giving rise to its linear shape. Another example of a linear molecule is carbon dioxide. The electron clouds around carbon are also linear, 180 degrees apart. It doesn't make any difference whether the bonds are single bonds or double bonds or triple bonds. Each bond, single, double, or triple, occupies the same region of space, and so there are only two electron clouds around the central carbon, 180 degrees apart, giving rise to a linear molecule. If a central atom has three electron clouds around it, the arrangement will be a flat triangle called triangular planar with bond angles 120 degrees apart. BF3 or BH3 or BCl3 will adopt such a geometry. Here's an animation of BH3, 120 degree bond angles with a triangular planar geometry. With four electron clouds getting as far apart as they can from each other in three-dimensional space, the bond angles will be 110 degrees, and the structure is called tetrahedral. Methane is an example of that. It's got four single bonds about 110 degrees apart. If an atom has five electron clouds around it, they'd be situated as depicted here. So we have three electron clouds arranged in a flat triangle, and those are called the equatorial positions, marked E. The bond angles are 120 degrees apart. But then two other electron clouds would be situated above and below that plane in what is called the axial position. In the triangular bipyramidal geometry, there's more space in the equatorial positions for an electron cloud than there is in the axial positions, as you can see by the bond angles. And thus, larger groups will preferentially be found in the equatorial positions. Let's take a look at the animation. Phosphorus pentachloride is an example of a compound that has five electron clouds around a central atom, phosphorus. This is the triangular bipyramidal structure. The name derives from the fact that we would have a triangular pyramid on top if we covered in the surfaces and a triangular pyramid on the bottom, and so the whole structure is referred to as triangular bipyramidal. If a central atom is surrounded by six clouds of electrons, they'll be 90 degrees apart. This is called octahedral. It's octahedral because if we enclosed it, it would have 8 surfaces. There'd be a square pyramid on the top, and a square pyramid on the bottom, 4 surfaces on top, 4 on the bottom. Let's take a look at an animation of SF6, which has this structure. Notice it doesn't matter which way you rotate the octahedral structure, it's the same in every direction. Now there are atoms, particularly transition metal atoms, that can have up to 12 electron clouds around the central atom. And I've shown here an example of 7 electron clouds. But for the purpose of this unit, we won't go beyond 6 electron clouds. An octahedral structure is the maximum situation we'll consider. Page 131. Here are 3 molecules, methane, ammonia, and water. And in all of these, the central atom is surrounded by 4 electron clouds. And so the arrangement of the electron clouds is referred to as being tetrahedral in all 3 cases. In the case of methane, 4 electron clouds are actually bonded electron pairs. And so the arrangement of hydrogen atoms around carbon is also tetrahedral. And the arrangement of the atoms around the central atom is referred to as the molecular geometry. The arrangement of the electrons around the central atom is referred to as the electronic geometry. In the case of methane, they are the same. But look at ammonia. Ammonia has 4 electron clouds around the central nitrogen, but one of them is a non-bonded pair of electrons. Although the electronic geometry is still described as being tetrahedral, its molecular geometry is described as being triangular pyramidal. The animation doesn't show the non-bonded pair of electrons on top. We do see the arrangement of the 3 bonded electron pairs around the central atom, and so its molecular geometry is described as being a triangular pyramid. A water molecule has 4 electron clouds around the central oxygen atom, so its electronic geometry is described as being tetrahedral, but its molecular geometry, the arrangement of atoms around the central atom, is described as being V-shaped or bent or angular. Bonded electron pairs tend to be thinner and take a little less space than non-bonded electron pairs. The electron cloud in a bonded electron pair is being shared between 2 atoms, whereas the electron cloud of a non-bonded electron pair sits entirely on the central atom, and so it's a little fatter, and so it tends to compress the bond angles of the bonded electron pairs. In the case of ammonia, with 1 non-bonded pair of electrons, the bond angles are compressed from the normal 110 degrees down to about 107 degrees. In the case of a water molecule with 2 non-bonded pairs of electrons, it compresses the bond angle down to about 105. Irregardless of that, the electronic geometry of all 3 of these structures is still classified as tetrahedral. So that's Vesper, valence shell electron pair repulsion theory. We want to also consider valence bond theory. Page 132, please. Valence bond theory. So before we apply Vesper to a variety of molecules, we also need to consider how bonding occurs. Vesper does not attempt to explain bonding mechanisms, but valence bond theory, VB, does. So valence bond theory is simply an extension of what we already know about bond formation. Covalent bonds are usually formed between 2 atoms by the overlap of 2 half-filled, singly occupied orbitals of the bonding atoms. Look at hydrogen. 2 hydrogen atoms form a covalent bond by overlap of their half-filled 1s atomic orbitals. And that forms a hydrogen molecule that is stable because the electrons spend most of their time between the hydrogen nuclei, drawing them together. Now in the case of hydrogen, the bonding atomic orbitals are half-filled, and they're suitably shaped to overlap, but this is not the case for most atoms. According to valence bond theory, atomic orbitals are hybridized or mixed together and changed to facilitate bonding whenever the atomic orbitals are not correctly shaped for bonding, so they'll be reshaped to facilitate overlap. And why not? They're just electron clouds. Why can't they distort their shape to do so? And hybridization also occurs when valence electrons are not suitably distributed for bonding. If we don't have half-filled orbitals, then electrons are redistributed to create half-filled hybrid orbitals for bonding. Now this hybridization, reshaping and promoting electrons, it requires energy, but in most cases this is more than offset by the stability gained by effective bonding that occurs after the hybridization. So we're going to look at examples of hybridization in a variety of compounds as we study covalent bonding in terms of Vesper and valence bond theory. As we consider various types of chemical formulas, we'll use this notation. A, B to the X, U to the X, and A represents the central atom, B represents an atom that's bonded to the central atom, and U represents an unbonded electron pair that's on the central atom. So we'll start with a compound of the type AB2, such as beryllium hydride or beryllium halide. So A represents the beryllium central atom, and then B2 represent two bonded atoms, in this case hydrogen or halogens. Start by writing the electron configuration of the elements involved that are going to bond. So chlorine, like all halogens in group 7a, have the electron configuration S2, PX2, PY2, PZ1. They have a half-filled PZ orbital that's readily available to form a single bond with any other atom. However, beryllium, element number 4, is in group 2a, and it has 2 electrons in the valence shell, 2s2. So I've drawn it here. These 2 arrows represent the 2 electrons in the 2s orbital of beryllium. Now beryllium does form a compound BeCl2 with 2 single bonds. But according to valence bond theory, the electrons are not suitably arranged to do that. We need 2 half-filled orbitals. So valence bond theory proposes that beryllium, in order to accommodate bonding, will mix together its 2s orbital with one of its empty 2p orbitals and create 2 new hybridized orbitals. Here they are here on the right. So we mixed together 2 orbitals and we got out of it 2 orbitals. But now the electrons have been redistributed. 1 electron moved to the next available empty orbital to create 2 half-filled sp hybridized orbitals. Now why do I call them sp hybridized? Well, that's the name we give them. What should we call them? They were formed by mixing an s orbital and a p orbital, so why not call them sp hybridized orbitals? And there are 2 of them. And now we have 2 half-filled orbitals in beryllium that are ready to overlap with the half-filled 3pz orbitals of the chlorine. And I'm just going to show that overlap by drawing a line between these 2, like so. And that represents the covalent bond formation. Let's look at this a little bit more. So this diagram represents the shapes of the p orbitals. The px orbitals, the py orbital, and the pz orbital. We're saying that px orbitals and py are full, but the pz orbital is half-filled and can overlap with a hybridized orbital of, say, beryllium. So if this represents beryllium's hybridized sp orbital, beryllium would be up here, and they would have another sp hybridized orbital overlapping with another p orbital from another chlorine atom above it here. This is chlorine. So that's beryllium's linear shape if you look vertically. These 2 here are sp hybridized orbitals that are half-filled and can overlap with the half-filled 3pz orbitals of chlorine atoms. Bonding in other compounds can be described in the same way. Cadmium bromide, cadmium iodide, they are also linear and they would be sp hybridized. Take a look at the electron configuration in this example. Let's consider cadmium bromide. Cadmium is in group 2b. It's a transition metal, so its electron configuration will be krypton, 5s2, 4d10. The d orbitals are full, and then 5p0. Now the d orbitals are not involved in bonding, so we're going to list it as krypton, 4d10, 5s2, 5p0. Let's write that out, and then we'll figure out how it's going to bond. So the electron configuration of cadmium will be krypton, 4d10. I'll move them out of the way first. They're not involved in bonding. The bonding, remember, is in the valence shell. That's 5s2, 5p x0, 5py0, 5pz0. I want to emphasize that the next available orbital is empty. Let's draw that. This represents the 5s2 orbital of cadmium, and it's full, 2 electrons. A little higher in energy, we have the 5p orbitals. We'll have 5px0, 5py0, 5pz0. They're empty. Now, the halogens, such as bromine, will all have, I'll just put here X for halogens, well, they'll all be S2, PX2, PY2, PZ1. So halogens have an electron distribution that's ready to form a single bond, like we've seen in HCl or a chlorine molecule. But cadmium, no, it's not prepared to form 2 covalent bonds. But let's propose, according to valence bond theory, that hybridization occurs. And let's say that cadmium mixes together one of its empty 5p orbitals with its full 5s orbital to produce 2 new hybrid orbitals whose energy lies intermediate between an s and a p orbital, because you're mixing together an s and a p. So the height I'm showing is between the s and the p. And each of these now will be half filled. This is hybridization. 2 orbitals have mixed together, they've been reshaped, and electrons have been promoted to produce half-filled orbitals. What do we call these hybridized orbitals? They're created by mixing together an s and a p. They're called sp hybridized orbitals, and there are 2 of them. What about the py and the pz orbitals? Well, yeah, they're still here. They're just empty. They don't really get involved in bonding. 5pz0. So now these half-filled orbitals can overlap with a half-filled orbital of bromine. Now I'm going to draw the bromine half-filled orbitals just as squares, just to differentiate. And each bromine will have a half-filled orbital. So here's one here and here. And they're going to overlap, and we form 2 covalent bonds. And that's valence bond's explanation of how cadmium bromide would form after hybridization of a 5s orbital and a 5px orbital in cadmium. On page 133, there's an attempt to show what's actually happening during the hybridization. So here is the full 2s orbital of beryllium and an empty 2px orbital of beryllium. We say that these will mix together, hybridize, and form 2 new orbitals, each half-filled. These are the hybridized orbitals made by combining an s and a p, so we have 2 of these sp hybrid orbitals. Now push them together so they overlap, their small lobes overlap over beryllium, and you'll see what this looks like. This is the shape of the 2 sp hybrid orbitals that are half-filled in beryllium. And they're going to overlap with the pz orbital of chlorine, one on the left, one on the right. Now the half-filled pz orbital of the halogens is generally considered to be adequate for forming single bonds. Therefore, we do not postulate hybridization of the halogens to form single bonds. Each of beryllium's 2 half-filled sp hybrid orbitals overlap with an unhybridized half-filled 3pz orbital of chlorine, producing a linear BeCl2 molecule. Now, BeCl2 and other compounds of the same type, AB2, will have a linear electronic geometry. That's the arrangement of electrons. It's linear shape of regions of electron density. And they'll have a linear molecular geometry, which is the arrangement of atoms around the central atom. Now, in the case of beryllium chloride, it has a dipole. Beryllium's electronegativity is 1.5 and chlorine is 3.0. The difference, the delta En, is 1.5. And here I've shown these bond dipoles pointing in the direction of the more electronegative atom, the chlorine. But the dipoles will cancel because they're equal in magnitude and opposite in direction, and therefore the molecule overall is nonpolar, and we would predict it's not soluble in water. So valence bond theory states that the number of hybrid orbitals produced is equal to the number of unhybridized atomic orbitals that were combined. We started with 2 unhybridized atomic orbitals. We produced 2 hybridized atomic orbitals. Why would it produce some other number? We just mix them together and reshape them. Hybrid orbitals are named by indicating the number and kinds of atomic orbitals which were combined. In this case, we mixed together one s and one p orbital. They were hybridized to produce 2 sp hybrid orbitals. Later, we'll see that if we mix together one s orbital and 2 p orbitals, they'll be hybridized to produce 3 sp2 hybrid orbitals. If we mix together one s and 3 p orbitals, they'd be hybridized to produce 4 sp3 hybrid orbitals. And if one s orbital and 3 p orbitals and 1 d orbitals are hybridized, they would produce a total of 5 sp3d hybrid orbitals. And in the final case, if one s orbital and 3 p orbitals and 2 d orbitals are hybridized together, they would produce 6 sp3d2 hybrid orbitals. So let's next consider a compound of the type AB3. An example would be BF3, BCl3, AlCl3, assuming that is in fact covalent. It's right on the verge between covalent and ionic. So its electron configuration is 2s2, 2px1. So I've drawn it here. 2 electrons in the 2s orbital, 1 in the 2px orbital. To form the compound BF3, valence bond theory says that boron needs 3 half-filled orbitals. Well, you can see it doesn't. It has only 1 half-filled orbital. Valence bond theory proposes that the 2s orbital is mixed together with 2 of the 2p orbitals to give us 3 sp2 hybridized orbitals. An electron is promoted from the full 2s orbital to the empty 2py orbital. Now boron has 3 half-filled degenerate orbitals. They're of the same energy, and they're available to overlap with the half-filled 2pz orbital of 3 fluorine atoms. What about the 2pz orbital? It's empty. It's simply not used. So here is a 2s orbital. It's spherical, mixing together with 2 2p orbitals and reshaping to form boron's 3 sp2 hybrid orbitals, each of which has 1 electron in it. That's what these arrows represent. I'll color them red here. There's 1 electron. Here's another one, and here's a third. Each of those able to overlap with the half-filled pz orbital of fluorine. The result is a triangular planar structure. The molecular geometry of the central atom would be triangular planar because there are 3 atoms or electron clouds surrounding it. The difference in electron negativity between the fluorine to boron bond is 4.0 minus 2.0, and that's 2.0, and that is very polar covalent. Boron is a metalloid, so it can't form an ionic compound with any element, but this is very polar, so there'll be pretty significant dipoles facing in the direction of the fluorines, but if you combine these vectors, they'll cancel, and so as a whole, BF3 would be a non-polar molecule. So that's a valence bond explanation of how bonding occurs to form the compound BF3. Let's consider a molecule of the type AB4, a central atom surrounded by 4 bonded atoms. Examples would include methane, carbon tetrachloride, silicon tetrachloride, and such. Start by drawing the electron configuration of the central atom. It's carbon in group 4a. Its electron configuration in the valence shell is 2s2, 2px1, 2py1, 2pz0. So here it is. Carbon has a full 2s orbital, a half-filled 2px, and a 2py. In order to form 4 bonds, valence bond theory says it needs 4 half-filled orbitals. It doesn't have them, right? The way it is, it can only form 2 bonds. So valence bond theory proposes that carbon mixes together its 2s orbital with all 3 of its 2p orbitals. 4 orbitals are combined to produce 4 hybridized orbitals, and they're Sp3 hybrid orbitals, and there are 4 of them. Carbon has promoted one of its 2s orbitals into the empty 2pz orbital to give us 4 half-filled Sp3 orbitals, and now they are in a position to overlap, form 4 covalent bonds with 4 hydrogen 1s1 orbitals. Here it is in pictures. A spherical 2s orbital mixes with the 3 2p propeller-shaped orbitals, giving us 4 hybridized orbitals. They are identical in energy. The term is degenerate. And they're identical in shape. And each of them is half-filled. Here's the 1 electron in each of those 4 orbitals, ready to overlap with the half-filled hydrogen orbitals. The geometry will be tetrahedral molecular geometry as well as tetrahedral electronic geometry. The bond angles are 110. The difference in electron negativity between a carbon and hydrogen bond, 2.5 minus 2.1 is 0.4. That's nonpolar covalent. And as a result, methane is a nonpolar molecule. It's insoluble in water and very low boiling. Page 135. Let's look at compounds of the type AB3U. They would have 4 regions of electron density, 3 bonded electron pairs, 1 unshared pair. Examples include ammonia and NBr3. Let's look at ammonia. In ammonia, nitrogen is the central atom. Its electron configuration is 2s2, 2px1, 2by1, 2pz1. Here it is. You see that nitrogen has 3 half-filled 2p orbitals. And you might wonder, why would we invoke hybridization to form 3 sigma bonds with hydrogen? Because it already has 3 half-filled orbitals. And that's true. But the problem is the shape. Take a look at this picture of the orbitals of a second period element, such as nitrogen. Notice nitrogen has 5 electrons. There'll be 2 electrons in the 2s orbital. Then you'd have 2px1, 2py1, 2pz1. Let's say that each of these p orbitals overlaps with a hydrogen. What would be the shape of the molecule? it would look like this. It would have 90-degree bond angles. That is not the shape of ammonia. The nitrogen-hydrogen bond angles are closer to tetrahedral. They're almost 110 degrees. So the shape of the p orbitals unhybridized does not explain it. We have to invoke hybridization. Okay, so how does that work? We propose that in nitrogen, the 2s and all the 3 p orbitals are mixed together. No electrons are promoted, they're just mixed. That's called Sp3 hybridization. We get 4 identical Sp3 hybrid orbitals. One of them has a non-bonded pair, not involved in bonding. Don't worry about it, just ignore it. And then the 3 half-filled orbitals overlap with hydrogen as expected. The difference, as we said, is in the shape. The Sp3 hybridized orbitals look like this, and they're shaped in a tetrahedral fashion. There's the non-bonded pair. Here are the 3 half-filled Sp3 orbitals overlapping with hydrogen, and there's the geometry of it. So the electronic geometry would be tetrahedral. The molecular geometry, which refers to the arrangement of the atoms, would be triangular pyramidal. There's significant dipoles in the nitrogen to hydrogen bond, and there's also a dipole pointing toward the electron pair from nitrogen. These dipoles don't cancel. There is a significant net dipole. Ammonia is a very polar molecule, very soluble in water. So valence bond theory does account for the shape. Now, we should point something out here. The hydrides of phosphorus, of arsenic, antimony, and even bismuth have bond angles that are quite close to 90 degrees. And since the electron distribution of these 5a elements, here they are, is suitable for forming 3 covalent bonds, and the measured bond angles of the hydrides of phosphorus, arsenic, and antimony are approximately 90 degrees, why are we postulating hybridization? The 90-degree bond angles can be explained better by the overlap of unhybridized, half-filled 2px, 2py, 2pz orbitals with larger group 5a atoms with small 1s atomic orbitals of hydrogen, as we talked about earlier. Okay, so take a look at the diagram here. I've drawn the hydrides of nitrogen, phosphorus, arsenic, stibine, and bismuth. So here are the bond angles. It's only ammonia that has bond angles close to the tetrahedral shape. For the larger central atoms, the bond angles are pretty close to 90. So why would that be? In the case of ammonia, the central atom is small, and the electron clouds, here's the non-bonded pair, here are the bonded pairs, well, they interfere with each other, and so getting as far apart as they can in three-dimensional space, by virtue of hybridization, it alleviates the strain of the interference of these clouds of electrons. But in the larger central atoms of phosphorus, arsenic, antimony, and even bismuth, well, these electron clouds are pretty small relative to the size of the central atom, and so it does take energy to bring about hybridization, so it's simply lower in energy and easier for the electron clouds to sit directly in the unhybridized half-filled orbitals of these central atoms rather than involving hybridization. I guess that makes sense, right? Now just be wary here. What I've just said, it only applies to hydrides. It does not apply to larger atoms like fluorine or chlorine or bromine, etc. Right? Let's go to page 136. Page 136. Let's look at compounds of the type AB2U2. That would be one central atom, 2 bonded atoms, and 2 unbonded pairs of electrons. Examples would include water and, for example, chlorine oxide. That would be dichlorine monoxide or chlorine 1 oxide. Now in this compound, the oxygen is central, even though it's more electronegative, and that's simply because, well, chlorine is monovalent here, and oxygen needs 2 bonds. Okay, so let's look at hybridization and bonding in this case. This will be for water. Let's start by drawing the electron configuration of the central atom. oxygen is in group 6a, 6 valence electrons. Here they are, 2s2, 2px2, 2py1, 2pz1. 2s2, 2px2, 2py1, 2pz1. And again we say, well, why do we need to invoke hybridization? Can't hydrogen 2 atomic orbitals simply overlap with the 2py1 and the 2pz1? Well, they could, except for the shape issue. Take a look again at the shape of p orbitals. Let's say this is 2px2, we'll put 2 electrons in there in oxygen. 2py1, we'll put 1 electron in the 2py orbital, and 2pz1. And then hydrogen can overlap, say like this. We'll bring its electron and overlap, and 1 up here. But what shape would that molecule have then? We'd have a right angle, 90-degree bond angle in the HOH molecule. And that's not the shape. Recall the shape is tetrahedral, or approximately thus. So the tetrahedral bond angle is 110, and because of the 2 non-bonded electron pairs, that bond angle is somewhat compressed, but it's still a lot closer to 110 than it is to 90. Right, 105 is only 5 degrees away from 110. It's 15 degrees away from 90 degrees. And so for that reason, we propose hybridization for the reshaping of the atomic orbitals into hybridized orbitals. We're proposing that the s orbital and all 3 p orbitals in oxygen combine together to produce sp3 hybridized orbitals, 4 of them, 2 of which are non-bonded electron pairs that are not involved in bonding, but then 2 of them are half-filled and overlap with the 1s orbitals of hydrogen to produce the water molecule. Here it is in pictures. A spherical 2s orbital combines with 3 2p orbitals to give us 4 sp3 hybridized orbitals arranged tetrahedrally, more or less. 2 of these orbitals are filled, they're non-bonding pairs. 2 of them are half-filled, overlapping with hydrogen. Now the difference in electronegativity of an oxygen to hydrogen bond is quite polar, it's 1.4, and therefore there are significant dipoles pointing in the direction of the oxygen. There are 2 more dipoles pointing toward the electrons from the oxygen, but the net dipole is still significant. It's a polar molecule with a high boiling point for its small molecular weight. The molecular geometry is described as being bent or angular or V-shaped, but its electronic geometry is still described as being tetrahedral. So VB theory is working okay so far. Now it turns out that the hydrides of sulfur, hydrogen sulfide, of selenium, selenium hydride, and tellurium, tellurium hydride, have bond angles quite close to 90 degrees. So this angle can be produced by the overlap of unhybridized, half-filled py and pz orbitals of large group 6a atoms with small 1s atomic orbitals of hydrogen. So sulfur hydride, selenium, tellurium, because the central atoms are larger, there's little repulsion felt by the hydride bonds with these larger group 6a elements, and so there's no reason to propose hybridization occurs. But with other larger atoms like fluorine or chlorine or bromine or whatever, then in fact the bond angles are again tetrahedral, so we're going to invoke our hybridization postulate. Predict the hybridization state of sulfur in sulfur dichloride. We'll start by drawing the electron configuration of sulfur. Sulfur is in group 6a, like oxygen. All right, hybridization. In order to form the proper shape of the molecule, we propose that in sulfur, the s orbital and all 3 p orbitals are mixed together and reshaped. They are hybridized. sp3 hybridization occurs we get 4 degenerate orbitals, orbitals of equal energy. 2 of them are filled, 2 are half filled. This is Sp3 hybridization. And the 2 half-filled orbitals will overlap with chlorine, and chlorine will have its 3pz orbitals half-filled. There they are, half-filled, and each of those overlap with the Sp3 hybrid orbitals of sulfur. What will that look like? Bent molecular geometry. But the electronic geometry is still described as being tetrahedral. Page 137, let's look at compounds of the type ABU3. That means 1 central atom, 1 bonded atom, and then 3 unshared pair of electrons. These would occur in, say, for example, HCl, or chlorine, or bromine, or iodine. Let's look at a valence bond treatment of the chlorine molecule. So here chlorine is in group 7a. Electron configuration is 3s2, 3px2, 3py2, 3pz1. So here are 2 chlorine atoms about to form bonds with those electron configurations. You notice that they have a half-filled orbital that's available to overlap. Furthermore, the shape of these pz orbitals is such that they can overlap to form a linear molecule, and in fact chlorine is a linear molecule. So it turns out for the halogens, if they're going to form a single bond in any compound, there's no reason to postulate that a halogen will undergo hybridization, whether it be a diatomic molecule or even something like HCl. Any halogen for that matter. We do not propose hybridization for a halogen that forms a single bond. Now if it's going to form multiple bonds, in fact we do, but for single bonds, no reason to. Turns out that all the diatomic elements, whether they be oxygen or hydrogen or halogens, they are nonpolar covalent bonds. They have no dipoles. In the case of chlorine, its boiling point is very low, meaning there's little attraction between the molecules because they're nonpolar. They're linear, nonpolar, low boiling. They have low water solubility. We're not saying that all diatomic molecules are nonpolar. HCl is polar, so the molecule is polar and it's miscible in water, but we still do not need to propose hybridization to explain its bonding. This looks like a good place to stop for this lesson, but we'll continue on page 137 in our next lesson.